Thank you very much. Let me start by thanking the organizers for a wonderful workshop and the guest fact with guides. Very, very much appreciated. I should also mention, I'm going to show some work that was done quite a while ago by former students, Stuart, Will, Li Yang, Shai, and then some recent work by Mitchell. This is the title of the talk, and let me go to the first slide, which dives in very well with Ili's wonderful talk we just heard and the last items that actually were asked. So essentially, I would say most surfaces in nature that the atmosphere interacts with are multi-scale, and many of them display scaling laws. So here's a photo of an Austrian alpine landscape. So there's a multi-scale mountain, multi-scale trees, and then I'll also talk a little bit about ocean waves with a broad spectrum of waves. So again, a multi-scale surface that the atmosphere interacts with. And I couldn't help but noticing that the logo of our conference, as you will see, the mountains are a little bit multi-scale, but the flow and the waves are actually single scale. And Ivana told us yesterday that artificial intelligence generated this. And I think the social scientists are actually quite worried that artificial intelligence essentially inherits the biases of society and builds it in a lot of the stuff that's being said. So as you can see here, AI actually generated not a multi-scale version of turbulence. I had to notice this. All right, so now I would say, and again, this ties in very well with Ili's excellent talk, is that most subgrid parameterizations we use are essentially based on single scales. And again, we have multiple processes. Ili had a wonderful list of the number of length scales, Z0, height of the boundary layer, height above the ground, mixing lengths, and so on. And of course, however, these are meant to represent that typically is the largest, the most dominant scale. And then when we have processes like this, then they represent kind of an aggregate effect up to that scale. And how do we do calculations when perhaps we want to somehow explicitly take into account the fact that there's a hierarchy of scales, but we want to somehow calculate things a little more accurately. So what I'll describe here is a sort of series of little works that we did that were actually inspired by renormalization group theory in physics, which the renormalization group theory, you have some effective parameters that you then say, oh, at this other scale, this parameter will be this much. Then you rescale it, and you have sort of a stepwise process, and that defines a map across scales, and then you look for fixed points of that map. And at the fixed point, then you have perfect scaling, and you get exponents and so on. It's been a very successful theory. Applications in turbulence from a theoretical point of view have probably not been as successful. So what I'll describe here is sort of inspired by this a way of doing simulations. So we call this renormalized numerical simulations. I should note that this is a bit similar to the dynamic subgrid model that's popular more in the engineering LES literature. So I'll describe the basic thinking behind it by an application. So it'll be very concrete, and I'll talk about essentially the application to fractal trees. And then I'll very quickly, because of lack of time, I'll talk about fluvial landscapes, multi-scale wall-attached roughness elements, ocean waves, and then hopefully I'll have a few minutes to talk about a sort of a separate item which has to do with non-equilibrium. This is another topic that was discussed yesterday quite a bit. And we've just kind of realized something which I think is kind of interesting. It's been only applied so far to moderate smooth surface for the more engineering boundary layers, but I think that there are implications for the things that we're interested in as well. And I'll describe this notion of the Lagrangian relaxation to equilibrium, which I think goes some way in putting to work a more formal way of separating between equilibrium and non-equilibrium. So hopefully I'll have time to get there. So flow of fractal trees, these are some large data simulations that Stuart did quite a while ago now. These are 3D simulations that were very expensive at the time, and the basic idea was, can we simulate or model something that's effectively as realistic as this? However, we only resolve the largest scale. So let's suppose we can only afford to resolve numerically on a grid subscales of the object, then we need to parameterize the rest. And in this case, of course, we built this highly sort of artificial object that is sort of perfectly scale invariant. And so that's the basic idea. Here's the sort of, well, this was pixelated, so this didn't come out very well. But anyway, this is what we'd like to represent. And here are some initial simulations that sort of tell you the challenge. So suppose you only are able to resolve the largest scale, so the trunk, if you will. Then you do the simulation and you measure the drag coefficient. Ultimately, that's what we're going to talk about, drag coefficients. So we measure the drag coefficient as a function of generation. So I'll call this generation 0. And we get, so this is branch resolved simulation. We get this drag coefficient. Then I add one generation of branches. I get a marginal coefficient, and I keep adding. And as you can see, this is a log scale. So the drag actually increases quite a bit. Of course, the smaller ones have less drag, but there's many more of them. So in fact, it's not obvious. And the simulation gave the black squares. If you just say, oh, I know the drag coefficient of flow over square cylinders, so I'll just put it there and I'll add them up. Then you get the red circles, which actually is different. The drag is actually a little less because of shielding. So the one branch actually shields the flow from the other, generates slightly less drag. So you needed the simulation to find this, but of course it's scale dependent. It keeps growing. And if you add, but it's a geometrically converging series. So if you add these the estimates based on known coefficients, you get this dashed line, which we would say, well, that's the limit when G tends to infinity. But how much is it really? Because already there's difference between the red and the black. You can approach this final sort of fractal limit actually from the other way, where I put a plate and I drill holes in it. And ultimately, if you do this infinitely many times, you end up with the same one. So now I can do simulation here, calculate the drag, and now if I put these holes, the drag increases. As you can see, there's a huge difference between the drag coefficient. So is there a way to do this affordably without having to resolve infinitely many scales and get the right drag coefficient with a finite number of generations? So that's essentially what the idea of the renormalized numerical simulations to do the following. We're going to represent the unresolved branches with a distributed force, and what we normally do when there's sort of a flow through porous media, for example. But what we don't know is the drag coefficient of the smaller scales. So what we're going to do is, while we do the simulation, we interrogate the resolved scales, and essentially we find the drag coefficient that we're actually computing from the big tree, and we apply it to model the drag from the smallest. That's essentially a very simple idea. But it's iterative and it's kind of cute because at the first time step, we don't have any. So at the first time step, let's say CD is 0, so I only have this big tree. Then I find the drag coefficient. At the next time step, I want to apply it as a model. And then in some sense, we're adding one generation of branches. But after a few time steps, you're essentially effectively adding many such additional coefficients. And so that's essentially what it is. So there's some technical details here. You have to divide the force into resolved force. This is the distributed subgrid force. And at every iteration, we measure the total force for the whole thing. We find the drag coefficient and then reapply it at the next time step to model the smaller scales. Now, notice that this drag coefficient, because the large scales are affected by screening and so on, they copy this to the smaller scale. So it's more physical than assuming a drag coefficient of a square bar. So yeah, so that's what. So finally, when we run the simulation with a single scale, so this animation has 2 scales, but we essentially run a simulation just with the trunk. And here's a picture of the velocity you get, so you can see copied this. You know, there's a mapping that copies the force and then repeats this pattern over and over. And then ultimately, the total drag coefficient is the green dotted line, which is actually, again, it's a little different from the red dotted line. And interestingly enough, it actually falls a little above the other one in this particular case. So now we have a very cheap way of generating drag coefficients of very complicated objects. And so you can, so we run this with 3D trees, things with Y's and so on. So here's a family of drag coefficients as a function of the fractal dimension of the tree for different types of trees. So there's the ones with sort of crosses, the ones with Y's and so on. They all have different coefficients, which can now be sort of calculated more accurately without having to resolve much of the geometry. So you have to, of course, know the mapping from one scale to another. So that's the basic idea. Now we've applied this basic idea to other things. So, for example, flow over multi-scale rough surfaces. Here, of course, we're used to characterizing this with the roughness length. And of course, as we mentioned, it's not always obvious what that Z0 is. So let's say we somehow try to relate it with the, let's say, the RMS of the surface fluctuations. that's in general not very satisfactory, but let's assume we did this, and we dump all our ignorance into a dimensionless prefractal alpha. So now the goal is to find this alpha. So what's the analog of what I just described? Well, the analog is that you have a numerical method where you're resolving, let's say, the largest scales of this corrugated surface, but not the smaller ones. And then you do something like this, where you say the total force of the wall surface stress plus the resolved part that comes from the product of the resolved pressure acting against the resolved portions of this Meneveau undulating surface. The sum of this should be the same whether I have a model expressed at one scale or let's say a coarser scale. And so here on the left is the LES resolution, and on the right is twice the resolution. So what's on the right I can get by coarse graining artificially after the fact of doing the simulation. I coarse grain the pressure field, I coarse grain the surface, I calculate this sort of fake resolved pressure drag at bigger scales, and I add it to my model that I would have had if I had it at bigger scale. And then I set these two things equal, and it gives me the equation from which I can actually find alpha. So in the end, what you're doing is something like this, where here's the log law, the equilibrium, something with the unknown alpha at one scale and the unknown alpha at the other scale. And I know the pressure at this scale, I know the filtered pressure and the filtered surface height, and you set these equal, and you have an equation that you solve for alpha. So we applied this to several types of surfaces that have kind of power law height distribution, so kind of scale invariant distributions. This is work with Meneveau, and Will Anderson, and we applied it. So they had generated some numerically generated fluvial landscapes using the Z equations. And then we tried several things with the flow perpendicular to the main channels, along the channels, and that's sort of a Gaussian hill distribution with this landscape. And essentially the idea is now you want to run simulations at various resolutions, and you want to get roughly the same results. So these are, so for example, I think in this case, interestingly enough, the best case was flow across channels, in which we compared simulations with 48 cube, 128 cube LES, and essentially in each of them, the total drag, if you will, ended up being the same, and we found a particular value of alpha and so on. For some of for example, the flow along channels, that didn't work as well. So here we had sort of a remaining scale dependence. So the method did work in some cases, but in some other cases it didn't, and there's discussions of the limitations of this and so on. But that's, again, the basic idea is that we're testing this approach by running simulations at various resolutions, that each of the resolutions we're doing this test filtering, finding alpha, and then applying it as a drag. So in this case, we find the Z0 based on this approach. Here is another effort on flow over kind of, I guess we'll talk a little bit about urban landscapes. This could be, I don't know, kind of, I think hangars, whatever have you. And again, we're going to assume some kind of scale invariant distribution. So there's a number of big ones and many more of the small ones and so on. So again, we ran simulations where we have one generation, two generations, 3 and 4 generations. Each of the little ones here is actually resolved on a grid. This is using a numerical code by a colleague. It's PICAR3D, so it's an inverse boundary method. And here, for example, our sample results, these are instantaneous snapshots of horizontal planes for the 4 generation one, and these are cuts at different heights. So at this height, you only see the big buildings, and then at lower, you start seeing the smaller ones, and then if you're very close to the ground, you see all the little ones. These are instantaneous visualizations of the mean. And then we essentially look at mean velocity profiles, and here is the equilibrium logarithmic region. This is the height of the biggest building. This is the next higher, next higher, next higher. And what we find is, again, this probably doesn't surprise anyone here, but very often in this field, people said, oh, all you need is the biggest buildings, the biggest roughness elements determines everything, and that's enough. That's the single scale. Well, then you get the blue. That's the G1. But if I go to G4, I get bigger, larger roughness length. This intercept here is going to be at a much higher Z0, more turbulence and so on. So adding the little ones actually makes a very big difference. In fact, we determined from these simulations the Z0, so 0 over H, and you can see, for the big buildings, because there's only very few of them, you have very small Z0, and it keeps on changing. It changes a lot as I add additional generations. And of course, now the question is, for the limit G going to infinity, what is Z0? And by the way, the 10% of the height of the largest buildings is up here somewhere. So it's lower. Maybe it'll get there. We don't know. So now the idea again is to apply this renormalized numerical simulation. Let me just fine. Thanks. So again, the idea is that I have a resolved part of the drag and the subgrid part of the drag. So the subgrid part is our general the parameterization in terms of the roughness length. So I measure the total drag, and I find a Z0 from the, if you will, from the total. And then I take that Z0 from the total, and since from one generation to another I have to divide by 2, I just set the subgrid part as 1/2 of the total, and then I redo it. So what I'm effectively doing is, if I'm doing a G1 LES with renormalized numerical simulation, at one time step, that's all I'm resolving. Then I measure Z0 from these two, and then I use it at the next time step, which effectively I'm copying this to smaller scale than adding these. And as you can see very quickly, you end up with the sort of representing the multiple scale all at once at every time step. So and ultimately you get a simulation. Now what we can now do is test again using this RNS. This type here. So if I add this model, whether I do a G1, G2, G3, G4, I end up getting exactly the same problem. So this is kind of grid resolution independent, even though explicitly I'm actually resolving all the scales. And then we get a Z0 that happens to be at somewhere in between, which we have known how to guess that ahead of time. So we have, this is just a single slide again, the same basic idea where you have the force applied at one scale consisting of the resolved pressure drag. So in this case now we're looking at surface waves. This is work done by Di Yang, former postdoc, also was working with Lian Shen on atmosphere-ocean interaction. So this is quite a nice code where they're resolving the waves on a deforming mesh, and we're doing an ABL calculation above it. And there's coupling between the waves and the wind. So the wind is driving these waves. There's a sort of a broad wave spectrum, so it really does look multi-scale. And what we do is, again, you need to parameterize the effects of the smaller waves that are not resolved on the grid, so they're not visible, but they should be there. And you don't know what subgrid, what roughness length to use. So again, you model it with some unknown parameter alpha times some measure of the roughness, the geometric roughness. So a parameter that you don't know times the geometric roughness, which you assume you know. And again, you equate the drag generated by the resolved and unresolved part at 2 scales, and you find alpha. You solve again an equation for alpha, and then you use that in simulation. So that was quite an interesting application. Okay, so now let me shift gears and sort of the final approach and topic. And here, this is a wonderful simulation that I was allowed to show here. This is from Tina Chow's group, and Julie Lundquist showed this at a seminar recently. So I asked her, can I borrow this animation, this picture from essentially a wind farm under strongly non-equilibrium conditions. So you have this sudden front hitting a wind farm. And essentially what I just wanted to draw your attention again to this incredible event where there's a very strong non-equilibrium. Right? So the wind is actually shifting direction, and then suddenly there's this burst, high speed coming along this. So, and of course, when you do these simulations, we're using similarity hypothesis that assumes equilibrium at all these points to parameterize the fluxes at the ground, for example. And the question is, what happens when it's strong non-equilibrium? So this is a lot of equations, but let's see if I can walk us through this. So what we're effectively assuming, and I'm going to forget about stratification or anything, so this is all neutral right now. when we assume full equilibrium, we're essentially neglecting all the unsteady transport terms, sometimes also the pressure and other forcings, and essentially we have that the total stress is constant, and that's also essentially we have this equal to 0. If you want to go to fully non-equilibrium, but we still want to have some kind of description of turbulence in the sense of unsteady Reynolds average and Navier-Stokes, what we're talking about is an equation like this. So we've added pressure gradient, but most importantly, we've added unsteadiness and the transport. So when we assume equilibrium, what we're really doing, right, we're saying that the velocity field is going to be, let's say, the friction velocity times some universal function. If we talk about log law or Meneveau, this universal function is not a function of y plus, which depends on viscosity, but y over z0 by, it's the vertical distance. That's what we're assuming here. That we're assuming that we have this function, but we have a friction velocity that is the representative of the momentum flux. And in general, and when we do LES, we don't know it ahead of time. We might know the velocity at the first grid point, but we don't know what this will start. Okay. So now let's make the assumption that we still make this assumption, but we allow this friction velocity to depend on position and time, which is what we're effectively doing when we assume equilibrium. This is actually what we're doing. So what we thought is, let's take this ansatz and put it in this equation and see what happens. So when you do that, it's quite interesting because, for example, a time derivative, you can write it as the time derivative of the friction velocity times some other things that are actually reasonably known. So for example, the time derivative of this, so the other thing I should say is we integrate from the ground to the first grid point of your LES. And then we plug in this assumed quasi-equilibrium profile. Then you get an equation that will have the time derivative of the friction velocity times the function itself and the scale and some little term. You can do the same for the effective term. And then you get actually some kind of velocity dotted with this horizontal gradient of this friction velocity, and this advection velocities can actually be calculated. So ultimately what we get when we do this is we get a PDE along the surface that represents the time evolving friction velocity that is now evolving in time and in space, and it's being advected by this. So it's like a Lagrangian evolution. And the right-hand side ends up looking like a relaxation at a time with a relaxation time scale Ts, where the friction velocity, which is the unknown, that's what we're solving for, relaxes to the equilibrium level. So in other words, we think of the equilibrium model as, well, if this was equal to this, that would be the equilibrium model. But if there's non-equilibrium, and you still insist on using equilibrium equation like the ansatz of the Meneveau or log law, well, then the friction velocity really needs to be plugged into an equation, needs to be obtained from an equation like this. And only when the time scale, when the turbulence is much faster than everything else, then this Ts will tend to 0, and then this actually tends to. So the equilibrium condition now can be seen as sort of a special case of an equation like this. So that's and so we've used this and we've gotten results and so on, but we're sort of out of time. What I thought I would show is more of sort of an analysis of data, that what happens if you insist on using equilibrium conditions and look at data. So this is taking direct numerical simulation of channel flow and filtering it at a sort of an LES length scale, and then plotting local profiles at single points as a function of the global friction velocity, and so there's a lot of scatter. So this does not collapse. So the assumption of equilibriums that there's a single universal function doesn't work if you don't do any additional time averaging. If you plot it instead of the global friction velocity, the local friction velocity is slightly better collapse, just locally defined friction velocity, but it's still not a good collapse. If you average over time at a time scale that maybe you think, oh, the dimensional analysis tells me the sort of the diffusion time scale of turbulence should be the grid scale divided by the friction velocity, it still doesn't collapse very well. But if you average in time over the time scale that we found, this relaxation time scale, which is actually the advection velocity times this, the non-dimensional advection velocity times this delta over tau, and you use the local friction velocity, now you get a perfect collapse. So all of this can be made to collapse if you average enough, which makes sense, right? If I average over infinite amount of time, all these profiles will collapse exactly this flow. But this is the sort of an intermediate time scale, but we got that time scale out of the equations through the self-consistency condition. So I thought I would mention this because the issue of non-equilibrium is also important. So let me close by my views of the most important things that probably doesn't really matter, but maybe I think in terms of challenges, I do think that numerical simulation is important, but I also think finding approximations, analytical approximations under more generalized conditions, still a lot of work needs to be done, and I think that's still of great interest. I mentioned this yesterday in one of the discussions. I think multi-scale couplings of simulations that are done at different levels of resolution. I don't know, coupling LES with warp and this sort of thing, I think it still needs a lot of more work. It's a really important problem. And modeling ABL with man-made objects, and again, I think a little bit with goes with what Eli was saying, that the generalizations of most is important, and we always, of course, we say it's often things are not applicable as too complex, but we should and we need to propose alternatives. And that's thank you very much.
Thanks, Charles. Quick questions.
Thank you, Charles. Nice work, nice presentation. And you show this drag coefficient is unknown, and you show the single trees. You added details, then dimension increases, and the drag coefficient increases. I mean, you put this, then drag coefficient increases. And that's wonderful. However, for the first drag coefficient, you know, we have some parameter to describe this structure of first, like LAI, leaf area index, or leaf density. Yeah, so how to translate your research language and modeling into the practical? Something in the LAI or
yeah, that's a very good question, and I should say the following. When we did the simulations, we purposefully picked trees in the wintertime, so there's no leaves, just to make it simpler. So this is more sort of a test of the basic idea. To address your very good question, I think I would want to apply this technique to trees that have leaves, that have little surfaces in addition at the finest scale, and then repeat these kind of calculations for that. Because only then can we really make a one-to-one correspondence. I mean, we could have calculated some kind of leaf area density for these trees, and we would have gotten some answer, but it wouldn't. I don't think it would be very meaningful, because I think leaves, in some sense, what the leaves do is they break the scale invariance at the smallest scale. So how to deal with that, I'm not entirely sure.
Thank you for the nice presentation. Mine is more a philosophical comment than, because we go more and more towards complexity and resolve a single tree and with the leaves or no leaves. And then I look outside at the complexity there in the real life. And then when we move these things from our exercise, numerical exercise, to numerical weather and climate predictions, I always wonder if all this complexity that we include and implement in our models stay or not within the uncertainty that the model itself has. And so while I understand this on a scientific point of view, because it's something that we like to investigate and we would like to mine reality as close as possible, but still, if we look at the larger scale and how much other uncertainties are there, I would like to see these kind of works be compared with the uncertainty that we have in general, so to understand how far we can go.
Yeah, no, I think, I mean, you're absolutely right. I think this is, think of this more as a, you know, we have these abstractions, you know, flat surface or this and that, and this is an abstraction in scale space. It's very abstract, right? It's very idealized, right? There's no trees like the ones I showed, right? Square trees and so on. But it's an abstraction in the scale space, that if we have an idealized case where we have multiple scales, then this is what you get. And again, I do think this can be useful to parameterize sort of offline, right? I'm not talking about doing this RNS as part of a weather model or anything, but offline you can pre-compute drag coefficients of certain elements in a different way.
Okay, I'm going to take 2 more questions, and then anything to say to the question. I think we'll just
Well, just to add on that, this last comment and also Silvia's sort of thought on that, your limiting behavior when you're going to very, very broad scales, that would include eventually moving targets, like if you think of that as an urban area or so, you're down to the parking lot, and then it depends in your parameterization whether or not there are cars there, or maybe people have changed to bicycles. So, is there any taking into account of that limits or of that limiting behavior?
Yeah, so I think the way to do it is to then stop that iteration and essentially use the value you got after. If I do this, let's say 6 times, my resolution range is now 2 to the 6 minus, minus 6. And then if I know that my cutoff is at that scale, then I just keep using that value I got, before. So that, yes, so the answer is yes. We haven't tried that, but it's absolutely true, right? It's the same in turbulence, where you get to the viscous range and now suddenly the K to minus 5/3 doesn't hold anymore. Typically we say, well, but the effects are dominated to the larger scales. So there are ways of further refining this kind of approach, but we haven't done that yet.
But would it always reach a sort of
an asymptote? I think that is something that when we started this, we did not know, right? We thought maybe this could divert, right? Well, how about it just keeps on growing or and so on. And in practice, this is all the cases we've looked at are actually convergent, so rather quickly, which actually tells you that the larger ones still are more dominant than the smaller ones. The smaller ones, even though you add more of them, the net effect is still smaller and smaller.
Okay, I have a question. You have a question, right?